Here's another talk on origami engineering. So origami can be used for two things, right? One is for thin-word structures, and another is mainly for mechanisms. And this talk will focus on mechanisms. So you can really imagine that origami is about folding, right? About deforming, about reconfiguring, right? So here's an example you can see. This is a solar panel or solar array in space. It's folded so it can be stored in the rocket like compactly. And while it goes to space, it can be expanded and into a large area so that it can absorb a lot of sunlight. So that's you can see there's origami pattern being used. That's how it can be used. So my researching postdoc was involving this using origami engineering to design some structures that can actively deform into different shapes. So let me just go into that, like what I did. So the topic, well, this is like the talk I gave last year, a long time ago. It's about design of multi-stable structures. So let me just go into like kind of details to explain like what it means and why we are interested in this, right? What does it have something to do with origami? So a bit of background. So multi-stable morphing structures are used in many areas. Here is an example. It's actually a cross-section of a wing, which is adaptive. So you can see there's some elements when it buckles, it's actually actively deforming. While it deforms, it changes the shape of the wing, so make the whole wing adaptable actively. And here's another example. It's also a bistable structure that can kind of snap into another configuration, which can close or open these air inlets, right? And then, okay, then the third example is actually our application. We worked on this for already. I worked on this for 3 years, and then there are people continuing. This is a collaboration like from 4 different universities. It's called Universal Electromagnetic Surface. Okay, the point or the kind of the idea of this project is this. So let's imagine we have a phased array antenna, right, which is put on a flat surface, which is represented by this. It can generate some electric currents and it can radiate some electromagnetic waves in this normal direction very well, and it can steer it a little bit, but it cannot see very well to the side, right, because of the projection area. It's largest in the normal direction, but it's minimum to the side. So the idea is what if this surface, of course there's something you can do to these currents. You can still steer it a little bit, right? This second picture here is showing that you can steer it, but still it's limited. So the idea is that, okay, what if this surface can just change into different shapes, right? Now you can, if for instance a cylindrical shape, right, you can see wider in this direction, or even a spherical shape, or maybe a hemisphere, so that you can see around very well with a wide field of view, but maybe low resolution. But later when you discern, oh, in that direction I'm interested, so you can deform back to flat and concentrate on that direction. So that's the idea. The idea is to have a deformable platform, right, for phased array antennas, and the platform can be deformed into different shapes, so that correspondingly the field of view of the antenna is changing. You can see wider, narrower, with different fidelities. Okay, so that's the idea. So here's the specific requirement for this reconfigurable platform, and where the origami comes can join in. So the requirement is we want the platform to be flat and to be cylindrical in one direction, and to be cylindrical in another direction, and to be spherical, right? It can deform in between these 4 target shapes. That's our task. So we're thinking of origami to do that, right? Because this looks like an origami thing. Okay, so here's our initial idea. So here's origami pattern, which is proposed by Robert Land, who is our collaborator. And you can see it. You follow this pattern. When you fold it completely, it becomes flat. It's more flat. You can see you can have 9 antenna tiles on top of it. And this geometry can be reconfigured into cylindrical 1, cylindrical 2, spherical. Great, it's doing what we want. Sounds we have a solution. And then the first task I did was to simulate the process, right? Because this is a high degree freedom mechanism. I want to see, okay, what's the kinematic path it should take to move from this configuration to, for instance, this configuration. So the first thing I did was to simulate it, basically to I programmed it in MATLAB and then did a lot of pathfinding stuff to just morph them into different shapes. So this work I also wrote it into an article which is written like given here. This is the reference. And okay, so but there's a problem. Okay, it's not solved. The problem is that for this small mechanism, it has 12 degrees of freedom, which requires at least 12 actuators. This is too many, far too many. Because when you have like a 5x5, it then will have, I've analyzed that, like has 24 degrees of freedom, so 24 actuators. It's just crazy, that's not possible. So the idea, okay, why it comes like from origami, multi-degree freedom mechanisms, and then to multi-stable structures. Here's the link. So the idea is say, okay, what if we can just transform this multi-degree freedom mechanism into a multi-stable structure, and that multi-stable structure somehow happen to be stable. I'm sorry about my language, but happen to be stable at all these 4 target configurations. Then we might just need to use a few actuators to just pull it out of one stable state and then just guide it to vaguely go into another stable state, and the energy itself will just attract it and help with a few actuators to guide it into another stable state, and it will stay there by itself, and then we can release our actuation. So that's the idea. So this is to transform a multi-degree freedom mechanism, which is very hard to actuate, right? Too many actuators for this case, right? For this kind of complex reconfiguration into this type of mechanisms into a multi-stable structures. This is our idea of simplifying the actuation. That's why we do it, right? We want to simplify the actuation. Okay, let's think about how is it possible, like how to do it, right? Like if it's possible, then how to do it. So so let's just frame our problem in a general way, right? Frame it as a design problem. So our problem is this, like given n target configurations, these are all prescribed, right? Cylindrical, spherical, flat, or this given. But now it's a mechanism, right? We can do nothing. We need to introduce some design parameters, which are in each hinge and fold, we introduce a torsional spring in it, which are designable. And the parameters are rest angles and the stiffness of those springs, which means we can pre-stress them and to make them harder and softer. Those are design parameters. And by just changing these springs, the properties, we hope that we can make n-target configurations. All of them are stable, make all of them stable, right? Which means without any external loads and actuator forces, it will just stay in all these n-target configurations. Okay, so is it possible? It sounds like a dream. So it is possible, okay, that's the result. So let me just illustrate why and how, where does this multi-stability come from, right? If you think about that, you have springs, which is a convex energy, right? But multi-stability is a non-convex thing, right? The energy is going up and down. How is it possible? Like where does this, like a non-convexity come from? Okay, it actually comes from the kinematics, because the kinematics is highly nonlinear. Okay, let me just show you what I mean by that, right? Through a simple example. Here's the example, a simple 4-bar linkage, right? 1 degree of freedom, and there are 2 torsional springs. And these two, they have equal stiffness, and the rest angles are at these 2 values respectively. And we only use theta A and theta D to represent our kinematics and our energy, right? And then we plot it in the configuration space, the corresponding configuration space, theta A and theta D, right? This is the configuration space. In this space, we can plot our kinematic path, which is governed by the 4-bar linkage. And we can plot another thing, which is the energy, internal energy, which are governed by these 2 springs, right? At these 2 points, right? You can see because the rest angles are at these 2 values, so the global minimum is here, right? In this plot, in this configuration space. And this is the energy contour, the equal energy curve, let's say. So it's cylindrical because it's equal stiffness, right? You can see it's going higher and higher on this. So this is the how we see this. You can see, yes, the energy is convex, right? You cannot, it has only 1 minimum, right? Monostable, cannot be multi-stable. But because these 2 phenomena, the energy and the kinematics, they are coupled, right? They are incorporated, they are mounted together, right? The springs are mounted on 4-bar linkage, right? They are, so the energy, the actual springs, like the values, the fold angles, cannot be here, there's a frustration going on. This is inaccessible because of the constraints, right? The kinematic constraints. So the value of theta A and theta D can only follow this. So if you follow this, you can realize, oh, it's actually bistable, right? There's a local minimum here, and then there's another local minimum here. So there can be multi-stability emerging from a simple convex energy and a very complex kinematics, and that's exactly what we have for those kind of origami stuff, right? If you think about it, yeah, it's possible to achieve multi-stability, and we just need to work out, okay, how to design it, right? If we specify, right now is we observe this phenomenon, right? You're given these designs, and we notice, oh, it's bistable, but how can we design for that? Okay, just let me go 1 step further to see how we can design. Let's say we specify, if we specify 2 positions, we want them to be stable, and then how can we design, what kind of springs, what parameters of springs we should use. Okay, so here's the design problem. Let's do it inversely. So given 2 target configurations, right, at these 2 points, let's say C1 and C2, same 4-bar linkage, but spring parameters now are unknown, right? Let's say the stiffness are still equal, but the rest angles are unknown. So what should be the rest angles for these 2 springs to make this structure to be stable at these 2 points? Okay, now it's very clear, obvious because of this drawing, right? You just draw firstly a tangent line, and then you draw a normal line, same for this. And then if they meet here, this should be where our rest angles be, right? Because if you put your rest angles here, you draw these circles, you can see, okay, this is a local minimum, right? But if this is a global minimum, and then if you have equal stiffness, right, this is another local minimum. This is how we do that, right? If we follow this, choose the 0 state, the rest angles at this position, then we have 2 local minimums here. If you have another C1 here, if you move C1 to here, you draw another perpendicular line, it intersects here. Or if you put the global minimum here, the rest angles value to be here, then you end up with these 2. So yeah, it can be designed, right? But this is graphic, right? It's easy, 1 degree of freedom, and in 2 dimensions. It's very easy, but we want to generalize it into a multi-degree of freedom, multi-dimensions, and so on, right? So that's our next step, but this is the core idea. So we kind of illustrate and explain it's possible, right? And how to design it. So the next step is just using some algebra and so on to express the tangent plane of the kinematic manifold at a given point, at several given points, right? Tangent planes. And second, we need to kind of describe the curvature of the kinematic manifold at those given points, so that we know which kind of directions we can take, like this so-called normal space or normal lines in this case. And then is the analytical part of this design, right? I just introduced very briefly, right? And here are the kind of the kinematic relationships, right? How these angles move, how the nodes displacement should be, based on these kinematic constraints. And also we have the energy, right? Once you move, right, your energy is changing, right? How it is changing. And then we put these two together, the energy and the kinematics together, and then we can write them into one formula. We can show, we can identify, right? Here's the first order energy variation, right? Which should be 0 if we want it to be in equilibrium. So we say, this needs to be 0, but not for mono equilibrium, but for multi-equilibrium, right? So this condition not only holds for one configuration, but for n configurations. Right, you can write a lot of similar ones and then pile them up together and solve them together. Then we'll satisfy multi-equilibrium. Right, that's how we do this. It's basically say, we take the take the tangent, and then the rest angle should be in the normal direction of that tangent, or in the orthogonal space actually. So that's one, and then another part is about stability, right? It took me quite a while to kind of get the stability right, because it's sort of complicated. I'll just introduce briefly, right? Like from an energy expansion, the second order terms is actually not enough. We're missing a lot of nonlinearity in this, it's very vague, but the previous this linearized formulas or compatibilities, linearized compatibility relationship. Okay, we missed a lot. But here are the two nonlinear displacements. The displacement is not a vector, right? It's actually a curve, right? You need to consider that the curvature of the displacement into the second order energy variation, and then you can get it right? The curvature of the kinematics, right? Also the rotation are nonlinear. Well, I don't want to go to details, but basically you need to do a lot of corrections, and this is the tensor, third order tensor, and you need to do a lot of I think it's kind of smart rearrangement, and in the end you can cancel and solve. So this is the nonlinear displacement. You can see there's a second order term for it. And also the nonlinear rotation, you need to include the Hessian matrix into it. Actually, it's also a third order tensor. So you pile them up, and then you find out, actually the second order energy variation is very complex. And then in this design, we need to solve to say, this term has to be positive definite. And then you can form it into a numerical, basically a constraint optimization problem, and you can solve for those design parameters, rest angles and the stiffness of those springs. So let's just go to examples which are more fun, okay? And here's one example. I say, can you solve to make this sort of kind of like a mirror origami, like to be bistable? So, here just how to solve it. And then, when you plot the solution, it shows, exactly two stable states and occur at exactly where I specified, right? This is my target. And then it ends up with exactly these two positions. And I also made a prototype for it. Here's how I made a hinge which you can post-stress it to exactly what kind of rest angles you want. So this is the design. You can see, you can just rotate, right? I think it's obvious. Also, I made some effort to reduce the friction, right? Some bearings, coatings, and so on. So here's a video to show it's bistable. Okay, is it playing? Oh, it is playing. So see, one stable state, and then you move it further, it's another stable state. Okay, but this manufacturing method is very complicated, heavy, and has a lot of friction. So we improve it by using another way of manufacturing. Okay, so a similar design, and then I'm using this called sort of laminar emergent torsional joints. Right, this is cut from one single plate. This is being proposed from this reference. You can see, but I modify it, make it, because in this case you cannot change the rest angle, right? You can only change its stiffness by cutting these beams thinner, longer, and so on. But it always rests at flat, at a 0 fold angle. But then I modify it so you can have a 180 rest angle. You can see, you can fold it up, and then the rest at fully folded. Here's another one. You can see it's resting at 90 degrees. So this one is also resting at 90 degrees. So now we shows using this kind of designs better than previous like torsional springs and all those shafts, which is heavy, complex, large friction. And now this is much nicer. It has the ability to design for both stiffness and also the rest angles of them, and also easy to manufacture, just cut. Okay, here's another mirror. We cut in water jet using spring steel, and you can see these two are kind of flipped. So okay, let me show you the video. Oh, sorry, it's a bit noisy. Can I turn on this one? So you can see here's another. This is the first stable state, and then you can see it's stable, just confirming. And if you push it further, it bounces out. Okay, it's another stable state. You can see it's stable. Yeah, two stable states. Okay, so move further, like to our project, right? We want to have an antenna, surface, cylindrical, spherical, right? I'll just quickly go to the prototype. So here is kind of a modified origami design proposed by Robotland, and then we kind of use our understanding of this multi-stability and also these new manufacturing methods by we're using water jet to cut this kind of spring steel, and then we end up with this type of structures, which transforms a 12-degree freedom origami mechanisms plus these novel joints we use, and then to a 3 stable states, how do you say, a platform, right? You can see flat, cylindrical, spherical. So there are a lot of sort of details in it, but doesn't matter. Just move on to this video. This is the actuation, right? So this shows only 3 actuators can morph it from flat. This is flat, you can see. From flat to cylindrical and spherical, and back to flat. So now this is it's a bit convex due to manufacturing error. Yeah, it took a long time to manufacture this stuff. I mean, yeah. So now I'm trying to pop it to be spherical. You can see it's gonna pop. Right, it pops. It's now spherical. Yeah, and if you can imagine, if you have antenna tiles on it, you can see all the way, like a wider field of view. So yeah, if you tighten another cable, only 3 cables, right? Yeah, only 3 cables. Yeah, you pull it, bounce back to flat. So, and I want to do cylindrical as well. Because sometimes maybe it's satellites going to the atmosphere. I want to see kind of this belt shape, right? We don't care about the other direction. So this is the cylindrical shape. You can see it's cylindrical. Yeah, now it has wider field of view on this direction, on one direction. Now it goes back to flat. This is flat. Okay, so it works, right? Now we don't need 12 actuators, we only need 3. So that's an improvement. And the conclusion is, yeah, using, okay, I think it's the first time people propose, say, oh, we can use multi-stability to simplify the control of multi-degree freedom mechanisms. So this is a innovation, right? We say, okay, here's a solution. Instead of mounting so many actuators, and which is hugely complex and expensive and maybe not reliable, we say, okay, using energy to help, right? Simple actuation, but we have multi-stable energy landscape. So we also propose how to do it, right? We say, oh, this is multi-stability, but we also say how to design for multi-stability. And also we have a set of analytical formulations, and also we correspondingly propose manufacturing methods, right? This is our contribution. Okay, I did this like for a long time in my postdoc. And also, so by doing this, we end up with a called an easy to actuate reconfigurable surface. And okay, the takeaway, or how to say, like my takeaway, like what I figured out during this process is that we should really embrace these multi-degree of freedom mechanisms, because this can help us to have minimum members. Because I worked also on another direction to try to reduce the degree of freedom, but it ended up with very complex mechanisms, right? Because you want to have a complex reconfiguration, right? You want the kind of degree of freedom to be very low. You need to add a lot of bars, kind of. It's very hard to design, and end up with like very like unrealistic structures or mechanisms. So that's, I think we should just embrace multi-degree freedom mechanism instead of make it to try to reduce it. It's very hard. Okay, maybe someone can do that, but I didn't succeed. So, but my solution is that, okay, let's give up on degree of freedom, but this will end up with something that's easy to manufacture, right? It's a very simple structure. It's not well constrained, right? Members of elements are very few. So, but we deal with this degree of freedom by sprints, by energies, right? We have energy landscapes in it to basically, how to say, diminish or kind of cancel all those degree of freedom, but instead we introduce the energy to guide the configuration into different ones, right? This is very easy to design, very flexible. We can shape this energy landscape differently, so the structure will have several preferred locations. And then the combination of these two end up with something that is easy to manufacture and also easy to actuate. So that's the takeaway. Okay, the corresponding research is being published into this journal, and then we wrote a paper. Okay, so at last I want to show you another example, which is what I did also in my postdoc, which is less academic but very interesting. Okay, I think it's cool. So it's another idea to make this surface, right? Instead of using previous, I mean, those very analytical ones. I mean, you can see this actually is one. I'll just introduce the results just for fun. This is actually one continuous plastic. I cut it as a panel, right? It's a continuous panel, and I cut it on laser cut, and I end up with this very beautiful. This is 7 by 7, and then you can see that it can work as an elastic plate. You can bend it into cylindrical shapes. Also, if you open them, it can be spherical. Right? This is it. It's even easier to manufacture. So, yeah, each structure was laser cutted by a single sheet, plastic sheet. So you can see 3 stable states. It has what we want. Okay, let me show you guys videos. Okay, this is flat. Only also again 3 actuators, 2 cables plus 1 slider. You can see this is flat, 2 flat. You can see it's on our structure. We have a kind of base for it. So we move this backing down, pull one. This is cylindrical in one direction. You can see cylindrical one, also cylindrical in one direction, and this is cylindrical in another direction. You just pull one cable. Okay. Now you can see it's bouncing up. It's snapping up, open. Right. This is spherical. You pull it and then snap. Okay, spherical direction. And yeah, you can see this just another way of doing it, right? Instead of using previous one. This actually is even easier to manufacture. Yeah, and also more stable actually than previous one. This is also lighter. It's very light. So this is another idea of doing these reconfigurable surfaces. This also can do like other shapes and tile, other surface shapes and tile shapes. These tiles are all square shaped. So this type of conceptual design, another one, like different but same purpose, end up with a structure that employs this type of joints. Well, you can see these joints are, like these joints. There are some special joints. I call it LRBT joints, and yeah, and also it's also a multi-stable structure, easy to actuate, easy to manufacture. So this work is also published, it's accepted, and it will be appeared in this journal. And then I have several other co-authors work together. We'll get this done. So yeah, it's another interesting one. So yeah, I think that's pretty much it.